Hello everyone, welcome back. In this video we will learn about the PKSIM user interface and we'll learn how to build a simple PBPK model in a PKSIM. So when you open up the PKSIM user interface, you get a blank page like this, and there's an interface available. So the PKSIM user interface is built upon this so-called building blocks, which is in line with what we discussed in the earlier lecture, that PBPK models are sort of a bottom-up approach where you put together different pieces together, and to build your simulations and then compare the simulations with your observed data. So let's learn about these building blocks one by one, and then we'll run some simulations and do some estimation and sensitivity analysis. Okay, so the first building block is this individual that you want to use for your simulations. So basically describing the physiology of the individual or even a population that you're interested in running the simulations for. So one note that in the PKSIM, some of the building blocks, just individual, population, compounds, and I believe formulation as well, has some built-in templates available. So you can either load from the template, or you can make your own person. So I loaded this standard European mail from the library, template library. So this sort of builds a physiological model for this standard European male. So if we go to the biometrics, basically it's just simple demographic parameters that you have to describe. I'm interested in making a European male, and if you select this population and gender, it basically pulls from this data set the mean parameters for that individual and populates for you. If you're interested in changing it, you can change it. I'll show you in a little bit how to do that. And click on the anatomy. This is sort of the organ volumes, volume of each compartment that we describe. We want to use in our model, and this is all built in. If you want to change anything from this, if you want to, let's say, make it into a minimal PBPK or extend this to include more compartments, you can do so in the MOBI extension, which is but sort of PKSIM, you cannot change the number of compartments and stuff, but you can change the estimates for these parameters. But I wouldn't recommend to touch any of this because these all parameters are very well established and studied. And there's some papers. I think I provided references in the first lecture. The Brown et al. Those goes in very much detail about the physiological parameters, such as organ volumes and blood flow rates, to be used in the PBPK models. And once, so this is all built in: the blood flow rate, GFR rate, the transit times, the pH of the gut compartments. Where the organ compositions, the fraction of each subcompartment. Let's say I have the, let's look at the brain. The vascular portion is 4%, intracellular is 96%, and the interstitial is 0.004. and then there's hematocrit level, and the plasma protein scale factor is mostly used set to 1. But if let's say some disease population, this can be adjusted for that. This is the pH level. If you look at the expression levels, in general, expression levels for the common enzymes and transporters are added in. These are enough, and for most of the compounds. But if you have something specific that you're interested in, let's say I want to do the transport protein OATP1B3, I can search for the levels in the database, and yeah, if you're sure this is the same gene ID, in this case we are, we can pull it out from this data sets, and then add it in. There it is. I have this, and I have to describe which kind of transporter it is, and this is an influx transporter, not the efflux. I'm going to delete it right now. So this is about a standard European male physiology that we added in from the template to later use in our simulation. So if you rather than describing a new individual, this is very cool functionality. You can scale from one individual to another. So let's say if I want to make it standard American female, I can change this to female. Let's say white American and female. It will adjust this biometrics from this data set. These are the half-life and basically the half-lives for the enzymes, some of the enzymes. And I don't want to touch those. It's gonna use the same ratio to scale. Same thing. I'm not gonna touch anything here. And the same thing for expression levels. Unless you're sure, don't touch it. And we got ourselves a standard American female to use in the simulation. You can also get the population the same way. You can even import a population data set if you have from the, but right now I'm going to just show you from the template, and it's pretty much saying you have the 100 individual, proportion of female is 50, the variability you can add I cannot change right now because we added it from the template, but if you're scaling or adding the new population, you can do so. And here I can add this parameters, and the same thing for expression levels. You can even add some variability in some of the anatomy and physiological parameters, or even the enzyme turnover rates and stuff. And the distribution, if you add some of the variability in some of the parameters, you can see those. But this is just because of we have the 100 people, and we have the different biometrics, so it adds in some variability just by defining the variability in the biometrics. Excuse me. Okay. So yeah, that's about the population. So next, let's learn about how to load the compound. So like I said, there's some templates. These are my defined templates, but you can, the predefined templates comes with the PKSim dataset. I mean, the PKSim OSP library, and you can use any of those or build your own. In this case, we'll make a model for cimetidine. So I'm gonna make the cimetidine model from a paper I have used. Okay, so I'm gonna so we'll define a PKSIM, the cimetidine PBPK model from this paper. Okay, so we're trying to recreate this PBPK model and then extend it a little bit. So the first, when you're building a PBPK model, first you need the physicochemical parameters. Sorry. So for that, when you find a paper for any PBPK model, it usually includes the physicochemical parameters. There are all online tools available like Chemicalize and the other one is I forgot what it's called, but basically you can predict this parameters from the structure. But for now, right now we have it. So the log MA is the membrane affinity. Usually you don't have the membrane affinity available, you have the log P, but for as a lipophilicity parameter, but membrane affinity is better in terms of describing the lipophilicity and to using the PBK model. The log P would work too. The plasma fraction unbound is about it's variable. It depends on the range of concentrations, but we don't really have that option right here to describe the variable. So I'm gonna just take 80%, let's say, and I have to say that. I have to mention if I'm using the percent or the fraction. And molecular weight is 252.34. 252.34. Paper. pKa is 7.1, which is basic. So we can put 7.10. The solubility is pH dependent. It's more than 2, but I'm gonna just put 2 because I don't really know how much more than 2 in the whole pH range, and I'll just keep it reference pH as 7. So in this paper, usually PKSIM basically calculates the specific intestinal permeability based on the provided lipophilicity and fraction unbound and all that. But a lot of time it does need to be optimized based on the data. In this paper they have optimized it, and there's some discussion on it, so you can read into it more, but I'm gonna put right now what they have optimized. I think I have it P intestinal. Okay, 5.15 10 minus 6. Okay. Oh, not this. Okay, I did this wrong. Calculated. Okay, I'm gonna add a new one. Wellman 2009, and I'm gonna make this default. And what was the number? 5.15. 15 E minus 6, and it was centimeters per second. Okay, and there we got ourselves the specific intestinal permeability. If we go to the distribution calculation, I always like to use Roger and Rowland, and sometimes if that doesn't work in the first try, you can try different options. The Pauline and Thiel also works very well, and PKSIM standard also works very well. But I always start with the Rogers and Rowland, and you can read more into these papers if you're interested and decide for yourself. And I'll keep the specific organ permeability as as a calculated based on the physicochemical parameters we added. So now let's think about the clearance mechanisms. We described our absorption and distribution methods, calculation methods. Okay, I think I had highlighted. Okay, so the primary route of cimetidine elimination is the renal excretion. About 50 to 80% is recovered unchanged in urine, and it's age dependent, but we're not going to worry about that portion right now. And a small portion is metabolized by CYP system, and I believe I read it from somewhere, some other paper, CYP3A4. In this paper, they had estimated the renal clearance by fitting to the data first 9.1 ml per minute per kilogram. But they also mentioned that since their focus was basically the absorption model, they had not used the elimination time points, like time points greater than 6 are not used. But in this case, we'll start with this value 9.1, and then we'll see how it works. So I want to go renal clearance, add renal clearance. I'll say I got it from Willman, 2009. Kidney plasma clearance, and it was 9.10 ml per minute per kilogram. And how it works in PKSIM is basically you can describe either the plasma clearance from the kidney, basically, and then you have your fraction unbound and blood flow rate and volume of the kidney, and then it calculates using this equation the specific clearance, or it's sort of a kinetic elimination rate. So if we add that, it'll calculate it, and then we say OK, and we added our clearance process. Since it said there's also CYP3A4, I want to add some, but I will optimize it if needed. Otherwise, we'll just leave it as 0. And there, we got ourselves a compound model. Now let's see how it works. So all this building blocks, the formulation, administration, protocol, and events, I usually add it when I'm running the simulations. So let's add the observed data first. So for that, I go to the observed data and then browse where my stuff is, my data set is. Okay, and then which kind of file I have. I'm gonna run the IV simulation first, so I'm gonna add this data set for the IV. We have to describe, define what is the unit. Okay, so there we go. Then we say import. We have to define which species and organ it comes from, the data that we have, because remember we are using the PBPK model, so we can even have the tissue concentrations, and we can use it for the model. But in general, okay, so we got our observed data in. Okay, so let me open that data set so we can look first. So this data set comes from, it was digitized from this paper, Larson et al. 1981, where the cimetidine 200 milligram IV bolus was administered to multiple patients, and this is the mean concentration time profiles in patients with normal renal function. I believe that there's a study in this paper. There was a study about difference between normal renal and renal impaired patients. So this is what we read it in, and so I'm gonna create a simulation for 200 milligrams IV bolus and see how it goes. To do that right now. So this formulation is more for the non-IV route of administrations. So we'll touch base on that when we do the oral. But let's add an administration protocol, which is 200 milligrams IV bolus, and we name it CME IV 200 milligrams, and it's a single dose. But if you want to add multiple dosing, you can use either this, or if you have more advanced protocol, you can use the advanced protocol. It's pretty self-explanatory, so I'm not going to go on that right now. Okay, so we got that. Now let's run this simulation and see how it looks. So I'm going to add a simulation, CME 200 milligrams IV, let's name it. We want to use our standard European male. Okay. This is all basically what we described earlier, what we want to use here. If you have multiple, there's going to be multiple options, like we had the specific intestinal permeability. There was a calculated one, and then we added Willman and added the default. So, but we still have an option to change anything it here. I'm gonna run the CYP3A4 optimized, but let's remember that it's set to 0 right now. And then we have our renal clearance. And there we go. And we have our administration protocol that we selected. We only have one right now, so we only see one in the drop down. And the events, this is more for like if you're studying the food effect, or and you want to add like different types of meal, you can add it from here, what time it was given, and the calorie levels and all that. So let's take that out right now. I'm gonna run it. It's creating the simulation. Here we got ourselves a simulation, but we haven't run it yet. This is sort of our PBPK model here. We have compound, we have the physiology parameters, we have distribution, and all types of parameters. And here's the reaction, basically the CYP3A4 as well as the renal. Oops, why did I close it? So then we run. When we first run a simulation, it's going to ask us which compartment we want to simulate this. So I have peripheral, venous, blood, plasma. That's what our data is for, so let's do that. Okay. So it always puts the micromole per liter, and I don't really like the micromole very much, so I'm going to make it to micrograms per ml and keep it logged. That's fine. Okay. Then we overlay our observed data. Okay. It does pretty good job, but it's still a little off here. So for that, like I said earlier, we could optimize some of the parameters. So let's try doing that. I'm gonna go to the parameter identification. So you say add parameter identification, then you have to add the simulation that you are interested in. And we have the observed data here, and the simulations. If you want to keep a scale log scaling or linear. And then next tab we define the parameters. We select the parameter. In the next step we select the parameters that we want to optimize. I'm gonna select intrinsic clearance for the step 3 or 4, and I also wanna, let's try that right now. If that doesn't work, we can try optimizing the renal clearance as well. So minimal value 0, maximum I can put like 10 maybe, and okay. So we want to use the Levenberg-Marquardt algorithm. There's also Nelder-Mead, which is the unconstrained, or you can use the Monte Carlo. Monte Carlo usually takes a little longer, so I keep the default. And let's say run. We can see how it looks right now. It's like a little window. There it goes. Okay. It didn't really change anything, and it still looks off. So I'm gonna add another parameter. Plasma clearance. And run it again. There you go. It looks better. Okay. There. So I like this simulation. You can even look at some of the diagnostics. And if I like this simulation and I want to put it into the simulation basically, so I can save it there. So transfer to simulation. Here it transferred to this simulation, but we want to also put it, change our building block to this updated values, right? So I click on this and commit to building block. So it will change this the parameters that we optimized here in this building block as well. So you can use it for the different simulation. We got ourselves the IV symmetry model. Now let's try how if we use this IV model and fit it to the Aural data and define the Aural absorption process. How does it look? So I'm going to add another observed data set. Okay, it's also in CSV file. It's this. Or milligrams per liter. To define that. Species human, peripheral venous, and plasma. Alright, so we have a data set. I can also run the simulation directly here and add the administration protocol directly. So I can do that. CMA, 300 milligrams oral. We have standard European male that we want to use. All this, we don't want to change anything right now. Anything? Nope. Okay, here we have to add that I want oral. Gonna name it 300 milligrams oral, and it's a single dose. Okay. So whenever you have the non-IV administration route, you have to select what kind of model you have or for your formulation. So here, if I want to add a new one, I click on this plus sign, and there's several options. There's dissolved. You can just say it's a solution. Viable function, it really works well it's very flexible function, and it works sort of well for defining various different types of absorptions. So I really like it. Or link AT, it's a little different version of the Bible. Or if you want like detailed particle solution, or if you have like deconvoluted like a the absorption phase, and you have the table with the fraction absorbed versus time, you can do that. You can add that. But I'm gonna choose Bible right now. See my Bible, and I'm gonna keep this default. But we, as I said, it's very flexible, and we can use it to fit it to various different types of absorption processes. Okay, so we have this simulation ready. I'm going to close the extra windows. We done. Okay, we got the absorption profile, we got ourselves the PK curve. I'll keep the milligrams per liter, and I'll add the volume. So this doesn't look good, so let's do the parameter identification. I'm gonna add that. And I want to add the oral absorption related parameters, dissolution time, dissolution shape, and I'll also add the lab time. Oh, we don't need the dose, sorry. Dose is not. Okay. For some of the parameters, it doesn't really like the 0 because it's not possible. So we have to change those. We can say 10 minutes is the max. And we can change it to up to 50 maybe. I like to use log scale. Okay, it doesn't like it. There you go. 1 minute, that's it. So that's our parameters. Let's say configuration, it doesn't change. We want to see the results. Okay. It's doing a good job. There we go. It looks pretty good. You can look at the residuals and predicted versus observed, all sort of diagnostics. But again, this is we just had the mean data set, and we use the simple curve fitting. We don't really have those fancy FOCE or like fancy population methods available here. And if it looks good, I'm gonna go with it. The results, I want to transfer it to the simulation. So now we have it here, and I want to commit to building blocks, so it gets saved here. Alright, so this is, we have a good symmetry model now. So now your homework is to find another data set aside from these two, and perform sort of a qualification of your model to see that this model works well if you want to use it for the dose extrapolation or the route extrapolation, or even if you want to extend it to the different population or something. Now let's run the sensitivity analysis of our parameters. Since we don't really have, for the PBPK models, we don't really have too many different types of evaluations or qualification methods. So to get good confidence in our model, we want to run the sensitivity analysis to see the uncertainty that some of our parameters may bring. So we go here in sensitivity analysis, and I usually add just all constant. It may take a few minutes to run, but if you are interested in some of the parameters only, you can also select and add those in. And let's say run. Show visual feedback. It's going to take a few minutes, so I'm going to pause this video and restart it when it's done. So now we have the sensitivity analysis done. So you can either see the results in the table format, or it makes a good plot for the parameters that it found to be most sensitive. So as far as in general, the sensitivity analysis criteria, if it's within -1 to 1, it's sort of acceptable. Beyond that, you may want to check the parameter that it's highly sensitive for. So here what we're looking at is if we, in the parameters, we selected the variation point 10, so 10%. So what we are looking at is if each of these parameters were changed 10% from its value, what would be the impact on the PK parameter that we are interested in. Right now we're looking at AUC 0 to end, 0 to last, and the ratio is basically showing here. So far it looks all of them within -1 to 1. Dose is the highly sensitive, of course, and that's expected. If you change your dose, your PK exposure is going to change. So that you can disregard. The scaling factor, fraction unbound, these are all as expected and nothing very striking. So yeah, that's about the sensitivity analysis. And I guess that's all for this video. So please don't forget your homework. Please try to recreate this while you're watching this video, and then try to search for the cimetidine data set in the literature. Try digitizing it. I'll put some instructions on how to digitize data set, and then you can use those observed data for an independent qualification of this model. That's all. Thank you very much, and I'll see you in the next video.